Hello.
Are you a student in the physics department?
No, I'm a biology student. My brother, who is a physicist at the physics department, told me about this biomedical talk, and I wanted to attend.
Oh yes, you're the, what is his name? I don't know him personally, but I heard
Joseph?
Joseph. Yeah.
Oh, both of those are my brothers.
Both of them,
Jack
yeah.
and Joseph.
Yeah, I heard the both. One is in electrical engineering, no?
Yes, my name is Hannah.
Okay. Yeah, nice to meet you. So what year are you in biology?
I am in my senior year technically, but I have 2 semesters left because I had
Okay.
some credits before attending. So yeah.
Oh, that's nice. Hi guys.
Hey, how's it going? Hi, Hannah. Hi.
Hi.
Yeah, you see a Tori in the background.
Hi, Tore.
Hi, Mihai.
Doug, I wanted to ask you is when Yasheng said we're gonna meet on Monday, I assume he implied via Zoom, no?
Oh, is it?
Because it's almost like he implied we're gonna meet in person, but I was like, I don't think he's here, no?
No, he's here. He is here.
Oh, he's here. Oh, okay, okay.
He came in yesterday, and so I was like, oh wait, hold on.
Okay.
Okay, so welcome to the Friday afternoon physics colloquium. We're very pleased and happy today to have Dr. Mihai Gherase from California State University, Fresno, giving a talk. Mihai began his educational career at the University of Bucharest, where he got both his BS and MS degree. Then he moved on to Carleton University in Ottawa, Canada, where he got his PhD in medical physics. He's been with us since 2014 and was recently promoted to associate professor. He's been very successful with NIH grants, publications involving students in research. And today he's going to talk about X-ray fluorescence methods in vivo bone lead concentration measurements. So Mihai, take it away.
Thank you, Doug. So let me see if can everybody see my screen?
Yes, we do.
Okay, great. So today I'll give you a brief account of my research for the past, say maybe 3-4 years. This is the main was the main project of the NIH grant, which looked into lead in bone. So I'll give you a bit of, introduction to why is lead interesting, and it's been interesting for the past few decades. You probably heard of it, at least, on the news or somewhere. I'll also give you towards the end a bit of information of what we did here regarding lead and with the XRF setup we have in our lab. So just to start off, lead has been known as a toxic element since ancient time. If you look at Hippocrates, described the lead colic, which is basically a severe lead poisoning in 370 BC, so a long time ago. Gaius Plinius also reported poisoning of lead workers. What we know now is that lead is not an essential element. In other words, it doesn't have any metabolic role that, at least that we know of so far, and is really considered a well-known toxic element. There is also a consensus, and that's been probably for the past maybe 10 to 20 years among clinician researchers. There's no threshold for lead toxicity. Some elements, some other toxic elements or substances sometimes have a threshold for which they become toxic. Lead doesn't have that, so it's something to keep in mind. In terms of why is lead toxic? It's a big subject, kind of a bit outside my expertise. When it's in the body, when exposed to lead, there are broad range of biochemical, physiological, and genetic dysfunction. But the one that's more important in recognized, especially for very low exposure to lead, is the nervous system. So it's considered perhaps the most sensitive targets of lead exposure. And the main mechanisms for this are the fact that lead can substitute the calcium 2+ ions, which basically have a regulatory actions in the brain cells. So that's kind of, if you read through the literature, that's kind of the main message that you get, that lead being able to replace chemically calcium, it affects the nervous system that way. And especially in the neurodevelopmental stages of the nervous system, it's even more toxic than in the later stage of adult life, where your nervous system is already developed. How do we usually assess if we're being exposed to lead, or what are the kind of the metrics associated with lead? There are two ones. One is blood and one is bone. I'll give a bit later a bit of information on what is lead in bone and how is in blood. However, the common denominator is the blood levels, and they usually, or what we call these BLLs, blood lead levels. And the usually number that is now in circulation is that for children, that should be, for the safe side, below 5 micrograms per deciliter. So that's kind of a number to keep in mind. Now, again, more about lead. How do we get exposed to lead? Well, first of all, if you look at the elemental distribution in the Earth's crust, lead is one of the fairly common ones. You see it here. Of course, there are much more common ones, but it's not quite of the rare ones. Now, if you look at the silver here, and other more platinum, they're much in much lower concentration. So lead is pretty high up here. There are usually a few exposure pathways. One is skin contact. So if you ever see a lead object, speaking of that, we used to actually play with lead when we were kids, and people who used to fish actually used to touch that on a regular basis. At the time, I think it was not quite recognized, or maybe not as known, that lead, even by touching, you can actually be contaminated. Another one that was actually really common until not too long ago, maybe 20, 30 years ago, is the aerosol. So, and that mostly came from lead in the gasoline. And then one you probably heard of it is the drinking water, via lead pipes. And again, we're something that we're trying to move away from all of these exposure pathways. The lead exposure has basically, it's been always there, as you've seen from antiquity, but has continuously increased since the beginning of the industrial revolution, somewhere in the 18th century, and kind of reached a peak somewhere in the 1970s. And the peak has to do with, there are a few ways where this peak came about, mostly through industrial, pollution. But one particular one was the lead additives in gasoline, lead-based additives. And these were added sometimes in the 1920s and increased in the 1950s with the increasing of the, car industry and, expansion of urban areas. Its usage, in, at least in US, was only ended in January 1st, 1995. Until that time, you see this graph here, which is taken from a paper, environmental paper, that in US alone, from 1927 through 1994, we released 5 million metric tons of lead-based additives. So it's not really like small amounts. They're a huge amount that went in the atmosphere, and they at some point they deposited on the ground, so around highways and other really highly exposed areas. We still have a lot of lead, and you see here the peak that reached somewhere in the 1970s, and then when we started to remove lead from the gasoline, it went down. So the human exposure, how do we assess this? There, as I already mentioned, there are two ways. One is you measure the blood lead concentration, and there are a few ways to do that. Mostly are the atomic absorption spectrometry, which is a bit less used now, but used to be used quite a bit 20 years ago. The most common one is the mass spectrometry method, especially the inductively coupled plasma mass spectrometry, where you basically take a small sample, you break it out in atoms, and then you measure the mass of those of the atoms. No, basically you ionize that and then you put them through magnetic field, and you can distinguish that. And that measures really, it's very sensitive. You can measure nanograms per gram, so it works really well. And then the other method is the bone lead concentration, no? And that is where we use X-ray fluorescence method, which I'll describe in shortly. So these are the two assessment methods. And now the question is, which one is the best? Well, obviously blood is a very simple one. No, you take a blood sample and you do it, and that's the most widespread clinical method. However, if we actually look at the lead kinetics, that's also been studied for the past 2-3 decades, is that if you get an exogenous exposure from outside, obviously the first, blood is the first, tissue that accumulates the lead. However, over time, you see, if you look at the lifetime in blood, it only stays about, weeks to a month at the most. And then it actually goes into the bone. So bone is the organ where you actually store lead, because again, you look back to that calcium, chemistry or mimic, similarity, and bone accumulates lead for a long time. Now it's usually much lower it's a fairly low concentration. If you look here, microgram per deciliter, which is roughly 0.1 microgram per gram in blood, so very low. In bone, it accumulates. It can go up to 5 micrograms or even much larger than that. For people who have been exposed, it can go even up to 20 micrograms or even higher. And it stays there for like years, even decades. And it takes bone takes about 95 of the lead you have in your body at any given moment. However, after, let's say, if you've been exposed in your use and then you retire, let's say if you worked in an, lead, toxic lead environment, after many years, you can actually the lead can actually travel back into the blood. So you can actually get another, if you want, like a second wave of exposure from lead that goes from the bone to the blood and can affect again your nervous system and so on. And then you have also urinary output, but urinary output is not as this issue is not as intense as other substances. So you don't eliminate it right away, again, because of that calcium and similarity and other metal similarity, that it really gets into the bone. So the bone is really the store for lead. Therefore, if you actually look at the two methods, you see advantages and disadvantages. You see for blood is a clinical procedure, relatively low cost, minimal invasive. You can use analytical lab, but is a metric of recent exposure. So if you've been recently exposed, it's fine. However, if you've been exposed over many years in very low doses, then the best one to do it is a lead bone, because it really reflects your cumulative long-term lead exposure. However, the disadvantage is that, first of all, you have to do an XRF measurements, which involves X-rays or gamma rays. So you do get some X-ray exposure. And probably the most important disadvantage that is not a clinical procedure. There are about a dozen research labs right now worldwide that measure lead in bone, but it's not really a widespread clinical procedure. So that's what our research kind of trying to go to make this, from a research kind of oriented measurement to a more widespread measurement, clinical type measurement. Now, if we look at the lead exposure assessment, if you look at the recent publications for the last 20 years, we notice a serious decrease from the past. Like if you look at in the US, we have these national health and nutrition examination surveys. And if you look at the 2007-2010 survey, they basically reported that in young children, there's been a 90 decrease from the previous, from the older one, 1976 to 1980, and where is probably a peak. And if you look at other countries too, like the South Korea study looked at geometric mean BLL in adults also decreased from about 2.37 micrograms per deciliter to 1.46. So you have everywhere. In Canada, it was actually the only bone-led study was done about 3 years ago. It came up to about this 3 years ago. And they basically noticed that about half of those in the same group, the level in the same age group was about half from the 17 years from the study they did previous 17 years earlier. So really, you know, like if you look just at these 3 papers, you see a general trend that, you know, the lead exposure has decreased. However, what we noticed more recently is that there is still a concern, and the main concern again relates to cognitive development of children. And if you look at some of the data, they show that basically you can have problems, developmental problems, even if you have below 10 microgram per deciliter. And in fact, in 2012, the CDC basically decreased the bar from 10 micrograms per deciliter to 5 micrograms per deciliter. And there are a few recent studies in China, for example, they did over 30,000 children study, and they basically noticed that there are about 9% of children, of these children who had the blood level higher than this threshold of 5 microgram per deciliter. And then there is concern towards other activities that occur, especially in developing countries, like electronic waste program and lead acid battery recycling. And these are like small kind of family type of activities where, you know, they recycle batteries or they try to extract, you know, useful parts of the electronics, and they get exposed to lead. And these are, you know, really not well regulated. Nobody really knows about. So that's another type of new exposure that has been revealed likely, and there are a few publications there to look at. So now I'm going to switch gears a bit and see how we can actually measure lead in bone. And we measure it with XRF or X-ray fluorescence. And to explain in, you know, in simple words, what is X-ray fluorescence? It's basically an atomic analytical method that is based on atomic excitation. And the reason is used the X-rays, the first word, is because we use this X-ray. So when an X-ray photon hits an atom, it can actually excite, it can be absorbed by a photoelectric effect. When it gets absorbed, because X-rays have enough energy, they can actually kick off electrons from any shell in the atom, including K shell, L shell, and so on. And when you kick an electron out, this is called the photoelectron, you leave a hole. And with this hole, the atom is basically in an excited state, and it's, you know, starts through a few processes, starts to go back to the ground state. And there are 2 processes. One is if the electron from a higher shell comes and occupies this vacancy, it emits a characteristic energy photon, and also in what we call X-ray fluorescence photon. And this photon has a very unique energy, which is unique to that particular atom. So it's like a fingerprint of the atom. Then there is another process where you actually have kick an electron in a higher shell. So again, it's an energy dissipative process. The problem with Auger, and that's called Auger electron emission, and its energy is also specific to the atom. The problem with that electrons, you know, interacting so strongly with matter, are very hard to detect. So if you look at surfaces of a sample, you could probably measure that energy, and then you can detect, you know, whatever atom they came from. But XRF is more practical because X-ray can penetrate, and they can actually, even if you penetrate deep in a body, like in our case, the bone, you can still see, that XRF photon can still be detected, can still come out of the sample. And then here on the right-hand side, I have like fundamental, you know, process why XRF works. If you look at the blue line here, that's the cross-section, or in other words, the probability of photoelectric effect. And you see that it actually beats out the other processes that we have. the coherent scattering or incoherent scattering. So it really is the most dominant at some lower energy. As you go higher in energy, the other processes become more dominant, but at relatively low energies and for, you know, atoms that are above, let's say neon, Z equals 10, all the atoms emit XRF photons. So they basically, in principle, they all can be identified with XRF. Now, just a very brief, I have put here kind of a not in a shell, not in a wall type diagram of X-ray interactions. What is the main equation or main law that dictates the X-ray interaction is called the X-ray attenuation, and it's basically an exponential law. And it's the same as light. If you actually look at light through a glass, you know, if you increase the glass thickness, you know, if you look at some, you know, thick glass, you'll notice less intensity, and that's known for a long time. It's called Lambert-Beer law in optics. Here we call it in general X-ray attenuation because it's an exponential law. So if the thickness here T increases, it exponentially it reduces the number of photons that basically goes through without any interaction. You know? And if you actually look at more detail at the mass, you can have these circles here representing the, you know, cross section. In other words, an area surrounding any atom you might have there. And if you actually look at the mass behind it, you realize that basically you can actually divide this mu, this linear attenuation coefficient, into basically cross sections. No, so the probability of interaction depends on how many atoms you have in a particular sample, how many circles, and what is the probability of that photon to hit basically that target. No, it's a basic concept in nuclear and, you know, atomic physics, particle physics. So that is basically what you can do for all these interactions, the photoelectric and the two scattering events. The only exception from this rule that basically only atoms matter in the composition to know how the X-ray is going to interact is the coherent scattering. And the coherent scattering is the basis of X-ray diffraction. You probably heard of it. And it really looks more of the wave type behavior of X-rays, no? Because X-ray, you can look at them at particles, but you can also look at of waves. So they have a wave-like behavior and a particle-like behavior. Here in XRF, we're mostly exploiting the particle-like behavior through photoelectric effect, but there is the wave-like behavior that X-ray diffraction takes into account. And that's actually also important. Coherent and incoherent scattering are important because you see them in the spectra. And basically, I'll show you here on the bottom here the two ways to look at bone, to detect bone. One is to basically kick out the electrons in the K shell, and the other one to have less, if you have less energy of the X-ray, you can kick out the electrons in the L shells here on the bottom. So basically you can have K shell transitions here, the ones in the blue, or you can have these red color L shell transitions. No, and you see there are different energies. However, those energies are fairly close. No, and you look here, this is the K betas. You see these little tiny peaks here in the K shell, and you see the elastic peak. This is the coherent peak, and then you see the Compton or the incoherent peak. So these are the three main interactions, and you see them both. Now, if you look at the pros and cons of the K shell, the pros are is that you have a high intensity, you have a high energy of X-rays, that but you also need a high energy to excite them. And unfortunately, you only have the Cu-109 is the only one that emits enough energy gamma rays to excite the lead. And you also need a germanium detector, usually larger, a bit more expensive. So it's a bit difficult for clinical application. However, it's been used quite a bit for human studies. Right now is the only one that was proven to work. L shell, on the other hand, is being tried almost in the same time. The upside of it is that you can actually use low energy. You can see the size of these arrows is lower. No, in fact, it's actually not to scale. The drawing is not to scale, but you need quite a bit less energy. You need about 10 times less energy. So you can actually use an X-ray tube. It can be made in a much compact form. You can use silicone detectors that are also more compact and usually cheaper. So it is better for clinical applications. On the other side, it has lower intensity, it has lower energy X-ray. So in other words, the attenuation through soft tissue that overlies the bone is a big problem. So therefore, the calibration has never been really, a calibration method has never really been resolved. And that's where our researchers mostly lying. I put here just a picture of how a KXRF that is quite established looks like. So basically, you see here, these are the germanium detectors. This device in particular has 4 germanium detectors. They're called clover leaf. And a person basically comes in somewhere in the mid tibia, puts the leg down. Somewhere here in this small, you'll see the Cu-109 source. So it's a 180-degree geometry. The gamma rays come and strike the bone. They excite the lead X-rays come and they are detected here. And all the other X-rays, the scatter X-rays and so on. The research of this lead in bone started somewhere in the 1970s, but most of the KXRF and LXRF were investigated throughout the 1980s. This system, this Cu-109, was developed in 1980, in the mid 1980s, and this system was the one that came out. And in the 90s, people already looked at in vivo. They already took measurements of, basically in persons, and there were several studies done with this system. Now, what we're trying to do is to use something much better. And you see here, this is a portable XRF, and you can actually buy a used one from eBay for about $12,000. So it's not too bad. However, the medical application of this XRF have really not been investigated. And as a postdoc, I used one of these for look at arsenic and selenium and lead, which are other type of trace elements that are of interest. However, they're mostly used for industrial. You can do lead paint expansion. You can do, environmental, agriculture. You can look at soils. You can look at all kinds of stuff. Wherever is there metal or something you can detect, you can look at it. And they're very practical. They actually work on a battery. You don't even have to have them, on a table or in the lab. They're practical, but they're not yet done. They're not optimized for medical applications. So when I came here to establish a lab, I already knew about this X-ray optics type technology, and this is my device here. So what it has an X-ray tube. It's not the portable kind, but it's a tabletop kind. So you can see the X-ray tube is here. It's cooled by air. Usually big X-ray tubes have to be cooled by water or even oil. So it's a bit when you have more power, you have a bit more problems with dissipating the heat. And what you see here on the right-hand side is an X-ray lens. And that's what makes this different from any other X-ray tube you buy, is because this X-ray lens can focus the X-rays to about 20 microns and at a focal length of about 4 millimeters. So you can really focus the X-ray in a very, very defined, very collimated beam. And that's what we call polycapillary X-ray lenses. And what they really are is just a bundle of several hundred of glass capillaries. No, if you look at them, you can look at them as basically as a optical fiber for X-rays. No, so but instead of being optical fibers are usually made of glass, and they're full. They're full of glass or any other optic material. These are actually hollow. They're basically air. And what really happens is when an X-ray from a defined source here on the left-hand side comes, if it hits that capillary at a very, very shallow angle, you can actually get one or two multiple total reflections. So that way you basically change the trajectory of the photon instead of being divergent, and you make it convergent. That's why it's called a lens. And here I have a formula for this type of glass, the borosilicate glass. If you look at this critical angle, it's very small. No, you have here the energy in keV. If you put 30 keV of X-rays, you divide it, you get 1 milliradians, which is really small. It's 0.06 degrees. So very, very shallow angles. That's why this lens is very long, because you get something, a very small, few microns, basically focal spot where the X-rays are emitted. And you basically try to converge them over a long distance. So the radius of this is very, very large. So you have very a relatively long X-ray lens. However, the advantage of having such an defined X-ray is that you can reduce the scatter, and you can really focus on whatever sample you want. So when I started to do this lead in bones, first of all, what you do is you don't start experimenting on people. You do what we call experiment on phantoms, which are basically tissue-like materials where you make them how to imitate a real tissue. In this case, we had to imitate the bone, obviously. So we put a bunch of these plaster of Paris, we dope them with lead. These numbers represent the lead concentration in microgram per gram or parts per million, ppm. And you see we went from 0 to a maximum of 75. This is much larger than what you'd get in a person, but you do have to get to a bit larger concentration in order to be able to see lead and get the calibration line from there. And then the other parts, the other anatomical parts of the problem we had to mimic is the soft tissues. Initially, we only work with this plastic, which is called polyoxymethylene. It's a dense plastic, but it really resembles well the skin. So the skin is the main part of the main tissue that covers the bone. So it's good to do it. But then we wanted to extend. So in the last year, almost 2 years now, we went through wax and resin. So we added 2 different materials. So having more different materials allows us to have a range of attenuations, which is expected to find in a real person. Or you have fat under the skin, you have skin, and you can have all this range. So we try to basically look at this. And so how we did it in this particular situation, because the beam is very small here, and it hits, let's say, the soft tissue, but then we have to move slowly towards the bone. And we found a way, and that was the work done with Summer about 2 years ago, 2-3 years ago, we realized that if we move in small steps, about 0.5 millimeters, we realized we don't need to do smaller than that. And if we look at the strontium, so initially, if you take only a 10-second, it's not enough to excite the lead. It's just the concentration is too small. However, strontium was in these samples, and it's also in the real bones. Strontium is actually an essential element, and it's in higher concentration than lead, and you always have it there. So we decided to use this to actually find out what is the optimal position we have to move the sample in the beam to find. And once we found that position, then we took longer trials, 3 by 300 seconds, so 600 seconds total. And then we actually saw the lead for pretty much all concentrations. And then we do these calibration lines, And from the calibration line, in a sample where you don't know the concentration, you can go back, and from the signal you get, you can compute the concentration. And we got this, you can get this for, let's say, for this plastic, you can put different layers of different thicknesses. You see how the calibration line slope goes down a lot with this thickness. You have here, the red one is 1 millimeter. If you put 4 millimeter, you the slope is almost 0. So you really decrease a lot. However, for the lead beta, which is the higher energy of lead, you actually still get a bit better. So these 2 peaks that you see here, the alpha and the beta has slightly higher energy, so it's a bit better. However, the background, as you see here under the beta, is a bit larger, so it overlaps with the scatter photon, so that's a downside. So we did these calibration lines, and from the calibration lines, you can actually establish what is the lowest concentration you can do, and that's what is called the detection limit. And one common formula to calculate that is to take the error on the lowest, on the 0, basically compute this from the spectra, what is the lowest, what is the error on the lowest. You multiply that by 3. Some people can multiply by 2. It depends on the statistical range you wanna do, and then you divide it by the slope of the calibration line, also, which represents kind of the sensitivity of your method. And then you determine the detection limit. And we computed that for all these 3 materials. And for clinical application, the consensus is that you have to have something below 10 micrograms per gram. If you have something below that, then you are getting to a useful range. But if you're larger than that, it's probably not useful. So if you look at the data that we have here for all the three materials, you kind of see that the soft tissue kind of has to be below 2 millimeters for any of the three materials. The wax, which is less attenuating, actually can definitely, be up to even 2 millimeters. But for the other ones, you kind of have to be below that. If you look at the people measure the soft tissue with ultrasound, and if you look at what people did, they saw that in normal, adult people, you have about 2 to 8 millimeters. Now in children, there's not much data, but it's known that children have a bit less soft tissue. So from this data, it suggests that probably children are the better suited subjects for lead bone measurements. And in fact, they are actually the most societal benefits from there, because they are the ones that danger for neurodevelopmental problems. Now, another problem we tackle, other than this detection limit and figuring out a better way to measure lead, was the calibration problem. That actually was, to me, or even more important problem than the actual detection itself. Also, detection is obviously essential, but the calibration was also bad, because in the past, what people did is that they used an ultrasound to measure the soft tissue. Then they used some general linear attenuation property of general soft tissue. And from the calibration sample, from the phantom, they extrapolated to any person or whatever sample we had, cadaver bones and so on. And they calculated the S alpha and S beta, these calibration line slopes. And from there, using the lead peaks measurements, they can calculate the concentration. However, when they compare their estimates with what was known in the bone, so they use other methods to measure the concentration of lead, they found that the LXRF, their method, didn't work. And the reason it didn't work, there are two things. First of all, ultrasound has not a very good, it's a very kind of slopey, has very large uncertainties for even the more newer methods. So the initial ones are in the 80s, but yeah, the newer ones, even the new ones, are not very, very good. Their error is still probably somewhere below a millimeter, but not much better, 0.5, 0.3 millimeters. So you still have that error you have to add on top of your measurement, so that makes it worse. And then probably the most important part is that your phantoms, the phantoms that they use in the past, didn't really mimic the soft tissue. You don't really know what the soft tissue, in fact, attenuation is. And because we work at such low energy, the soft tissue density and its exact composition of atoms is really important, becomes even more important low energy than the high energies, because photoelectric effect becomes more important. So what we decided is to use something that hasn't been much used in XRF. And one is that if you actually have an element, let's say strontium, it has usually two energies, beta, K beta, and K alpha. The ratio of that is actually an atomic, so it's also kind of like a fingerprint at the atom. However, as this alpha and beta goes through the tissue, they get attenuated because they have two different energies. They get attenuated differently. So when you actually look at their ratio, you don't see the atomic one that is known and is being measured. You actually see an observer with a larger one, and the larger one reflects how much attenuation in soft tissue. So in other words, it's basically an indirect measurement of the soft tissue attenuation. And what we did is we developed two relationships. I'm not going to go through how we derive that, but we basically look at the slope for alpha, for the lead alpha, in a particular thickness, and we correlate it with the one that has no thickness, so basically the bare bone samples. And then we took this ratio of strontium, and then we put this A alpha, which is basically a non-dimensional parameter. So we are able to basically find out the slope, or find the method to find the slope without actually doing any other measurement, without ultrasound or measuring its attenuation properties. We just simply use that. And you can actually see that these two equations, these linear, actually hold. If you actually take the logarithm on both sides of the equation and then you plot them here, you see it's pretty much a linear relationship. You see some variation of the data points, but it's pretty good. And then I basically, instead of using each material, I said, what if we actually take these two values for alpha and beta and take an average of all these three materials and just use this average across all the materials. So that way, no matter what type of soft tissue you have, you'd still find, a concentration. And we apply this for our phantom. We didn't do any, type of realistic bone, but we use it for the phantoms. And we recalculated using the data. We calculated the concentration and then we compared with the one we already knew. And you see here, the line here is the identity line. So basically means the all measurements and what it's, how well they correlate. And you see that there is a pretty good correlation. This is just for the resin. I have, data for, of course, for the other three. And then on the right-hand side here, you see, you see what the differences are, no? So this is what is called a Bland-Allman type plot. So you basically plot the differences and you divide it by the error. So within 2 error bars, you should pretty much have all your data. If some of the data comes out of that, then it means you have some bias in your data. And you see that you're pretty much going up and down around the 0 difference. No? So there is, statistically speaking, there is no difference between the estimate and what is known. However, if you look from the plots here, you see the error bars are, relatively large, but the measurements are also, the error on the measurements of the lead is really large too. So it's about sometimes 20%, sometimes even larger, because we are really still on the detection limit. We're very close to that. So, the error bars are large. However, you see that the identity, like even for 4 millimeters, we actually still get pretty close to the identity line, definitely within the error bar or 2 error bars. So to conclude, I think we got a different way to look at calibration, and I think that was probably the most important part that came out of the study. Another thing we did is that we can probably look at possible application for bone lead measurements in children because they have a lower soft tissue. So even if we have these lower energy L shells, we can still look at that. We developed this spectrometric calibration method based on strontium. We're looking at some lamb bone studies. We're trying to do that with a lower concentration of strontium. The one we had was a bit higher than normal, about 10 times more what you expect in a person. So we try to prove that this method could use even if you have lower strontium concentration. We also look at some radiation dose analysis. This work is still not finished, but we estimated the dose to skin would be about 3 millisieverts for about 16 minutes of radiation. The radiation dose to the bone marrow, which is a radiosensitive part of the tissue, is also conserved for children, but is definitely lower than the skin. So if these numbers probably don't mean much to you, what is a millisievert. Just to give you like an idea what the millisievert is, you see the KXRF, they also did a dosimetry study. They got about 23 millisieverts dose to skin. And the effective dose, which is basically the dose to the entire body, is on the microsievert, so another 3 orders of magnitude lower. And if you don't know what these microsievert or millisieverts, an intraocular radiography, so a dental X-ray that you take, has about 5 microsieverts. No, so that's kind of the range, and that's what the range of application has to be. You have to be on the ballpark of a dental X-ray. If you are above that, then there's some concern that what are the benefits and the risks. You always have to maintain that balance. And just on a higher range of dosimetry, if you look at the chest CT, if you have a problem with heart or lungs or whatever in the chest, you do a chest CT, you get about 7 millisieverts. So quite a bit higher, because we're talking about dose to the entire body, not just to a particular part. So just for future work, we were working, as I said, with this lamb bone. I think we can validate this calibration method, at least for strontium. We probably won't see the lead in that particular, but you can at least definitely validate that you can still measure the soft tissue attenuation. We have to complete some work on radiation dose, maybe look at the bone marrow dose, which we kind of didn't look much. And also there's some engineering work, which probably I won't do, but how you can actually change this portable XRF to make them usable to measure lead in bone. You have to change their geometry, because if I go back to how these guys usually look, they look like this. They're basically a 45 type degree. You know, you have the X-ray and then the detector is right there. So you have to modify a bit their geometry and modify their design in order to use them for and to also collimate their beam. So I'll just finish here with acknowledging all my students who work in my lab over the past few years. I think Danielle and Andressa was an exchange student from Brazil. I started working with them about 4 years ago, and then the funding from NIH and college and the department. And thank you. And if you have any questions, I'll entertain them.
Yeah, thanks, Mihai, for a great talk. Does anyone have? Actually, hold on. Actually, Hannah does have a question that she put in the chat, and it's like, you can look at it where it's like, so using the strontium that creates the K beta K alpha ratio basically prevents having to use the ultrasound, preventing inconsistencies in measurement calibration, question mark.
Yes, exactly. So ultrasound is being tested, I think, in probably 3 or 4 studies. The most important is in the early 2000s by a fellow, a colleague of mine. Well, he's a bit older than me, but he's still a colleague of mine from, he works at Stony Brook Hospital in New York. He actually is involved with Ground Zero research, but he's well known for bone lead measurement. In the early 2000s, he really tried this LXRF, and he actually, the final study they did is on cadaver bones. They took human cadaver bones, they analyzed them with ICP-MS, so they knew how much lead, and then they try to do their best to apply this LXRF and measure the soft tissue, use the phantoms, and then he, you know, in the end, when they compared, he realized that the method just didn't work. So, and that, I think, was probably the best and with the most detail. So our method using strontium, I think it's gonna work better. There is still a problem of detection, and that's, I think it's a fairly serious limitation, but I think for children that might actually work. Probably for adults, not as much. But again, because of the legislations and all the measures we take, we're not as much concerned, at least in developed countries, but even in developing countries, the exposure to lead is much less than what used to be a few decades ago. So the children are the ones who are more concerned now.
Thank you.
Yeah, you're welcome.
I have some questions about the photoelectric effect. Like earlier when you were explaining the mechanism on how it worked, I'm really thankful for Dr. Walkup's Quantum 100 class, because I was able to follow you there.
Good, that's excellent.
But so basically you're saying that electrons are being knocked off, because that's the basic idea of like the photoelectric effect. You're trying to like knock off electrons. So you're saying with the one with the characteristic X-ray emission, you're trying to say that you're knocking more electrons off closer to the orbital or like the proton center area?
That's the proton. Yeah, the one in the middle here is the nucleus, which has protons and neutrons, and the surrounding the red dots are the electrons. So yeah, with the photoelectric effect, the photon is completely absorbed. So its entire energy basically is able to kick off this electron. So the energy goes. So you're basically you work against the binding energy in the atom. So if you have a K shell, you have the most binding energy. It's the most inner core electron. And then you have some energy dissipated into this photoelectron, but the atom actually remains with a lot of energy because now it has a vacancy. So all this binding energy, which is actually negative energy, if we actually kick off the electron, the atom is actually in fact in an excited state. And then what happens after that, the atom tries to go back to the ground state, which is the the stable state and the lowest energy, the lowest energy. And then how it does it, there are two processes. And one is this characteristic X-ray emission, or XRF, where you emit basically another photon when an electron from an upper shell comes and fills this vacancy. or you can have an Auger electron emission, which basically is kick off another Auger. So it's still a energy dissipation mechanism, of the atom.
So just to summarize, the characteristic X-ray emission takes over the fact that you've just lost an electron by removing electron into another orbital just to fill up that excited state. And then the other one, and then the Auger electron is like, it's just, electron is just like removing another electron just to stabilize things?
Yes. Yeah. So all processes, and they are basically competitive. There is actually a probability, and it's known for each atom. Probability to get an X-ray fluorescence and the probability to get an Auger electron. In fact, if you kick electrons from higher shells, you're going to have more probability of Auger versus XRF. So XRF is better if you actually kick the K shell. That's why one of the reasons L shell is not as intense is because you actually get less XRF when you kick off an L shell as opposed to Auger electrons. The problem with Auger electrons, you cannot see them because they are very hard to detect. They basically attenuate within like microns. Their energy is low and they're electrons, so they interact very strongly with other electrons. So they're, you don't see them. While X-rays can actually penetrate through the sample, and you can see them and detect them. So that's why XRF is much. There is actually a method to measure this Auger electron energy, but you have to look at in vacuum. You have to put everything in vacuum because even air can attenuate those electrons, and you have to look at the very, very, very shallow micrometers type. People who do surface science can actually look at Auger electrons. So in fact, they can detect Auger electrons and they can measure what type of metals you have there. But those you have to have specialized equipment. It's actually much more complicated. XRF is quite a bit more practical that way.
I see.
And nice part about Auger or XRF in general is that it's a non-destructive sample, because all these atomic mass spectrometry, they actually destroy the sample. You have to separate in atoms in order to identify which atoms you have. These analytical methods. While XRF, you don't have to. Basically, this XRF photon coming out tells you that information of what type of atoms you have. So that's a major advantage when you look at biological and medical applications, because you don't want to chop a part of tissue out. But in blood, that's what they do for blood measure. They actually take a sample of blood, and then you don't need much. You need microliters. It's very, very tiny amounts you need for ICP-MS, but it's still a destroying sample. So if you actually look at a sample and you want to basically map the distribution, XRF with a very, very tiny beams, there are beams that now go to like micron size, you can actually map elements. And usually you do that at synchrotron. You can do it in my beam, but my beam is quite not as intense to do this because it takes so much long to basically map each point on a sample in a micron level type and get a map of elements. But you can do that at the synchrotron facility where they have these very strong X-ray beams, very collimated, very small, and you can do that in a useful time. Well, usually a couple of hours, but you can do it. You can map this. I have some example if you're interested.
Thank you.
You're welcome.
So actually, Mihai, I have a question. So you mentioned strontium as an essential element and lead is not. And so as far as I understood, the distinction was your body doesn't use lead for anything, but it does use strontium, yeah?
Yeah, strontium is an essential element. And in fact,
it's like actually calcium, right? It's
actually been very, strontium has been kind of in the spotlight in the last 20 years too, because there are some animal studies where they administer animals strontium granulate, which is an organic part of strontium, and they proved that it can actually combat osteoporosis, which is basically a bone demineralization process that occurs usually with age, and it depends on other factors. But and in animal studies, they show that if you administer strontium, you can actually combat osteoporosis. It actually increases bone density, the processes that increase and maintain the bone density. However, it's a bit controversial because there are some other animal studies done after which kind of show that no, it doesn't work. So it's a bit of controversy. But strontium it's also uniformly distributed in the bone. If you look at actually in the bone depths, lead has actually is more on the outer part because that is the most denser, part of the bone and tends to be there. So there are some synchrotron studies where they look at bone distribution, and lead is more on the outer, and then it decreases as you go towards the inner side of the bone. While strontium and calcium are pretty much uniformly distributed within the micrometer scale. They're uniform distributed. So that also helps. And it helps that they are in a much larger concentration. They're in the concentration on the order of like milligram per gram type per gram of calcium at least. So they're much higher than lead. So, and you can also excite the K shell because they are lower atomic numbers atom. With X-ray tube, you can actually easily excite their K shell. So they have, their peaks are much higher. Let me see if I don't know if I put in mine, if we see the actual, yeah, I probably didn't include here. If you go to the right-hand side of this, you see the strontium peak, which are much larger, like several times, 10 times more larger. So you can detect them easier. This actually calibration method would work for lead, but I think would work even better for strontium. I think it would actually be a better, because they had the same kind of problem with strontium too, is calibration of figuring out what is the attenuation in the soft tissue.
So any other questions, comments? No? Well, if
I
not,
do have a lot of biology-based questions. I have a couple. So I kind of was curious because one is just like how since you were talking about like exposures to children in lead, I was wondering can children get, or like children being born or like kind of like in the fetus actually get lead poisoning based off of if like say if a mother's exposed to lead and it's in her blood system. Like I know if it's like in her bone, it's probably not as much, but if it's like current exposure going in her blood.
Yes, they can get exposed. Yeah, one problem with lead, and I think there was a line here, that it actually can cross the blood-brain barrier. So it can actually easily affect the entire nervous system, as opposed to other chemicals that are blocked by the blood-brain barrier. The lead can go through it. So it's, yeah, it can affect, it would affect the baby if the mother will have, by whatever reason, a high concentration in the blood. And that would be certainly of concern, but hopefully it doesn't happen too often. But the concern is even for really low levels of even just from dust and people, kids playing like, or old houses have lead paints. You probably know that when they buy new old houses now, there is remediation process. They come with masks, and they do sometimes a chemical test, like just a color change with putting on the paint, or you can take one of these portable and shoot on the wall and figure out if you have a lead-based paint. All the houses are being built before, I don't know, 1970s or something. They all.
Yeah, I used to live in an old house that was before, like built 1950, like 19. I think it was like 1930 or something. It was like, I don't know. It's like it did have lead paint, and we had to deal with some stuff like that.
Yeah. So at least removing lead from gasoline and paints was a big, because that is most of the lead contamination for general population, not for people obviously who work in lead smelters and other type of activities. They can still get exposed, and hopefully, I mean, we're more aware, so we're trying to mitigate those exposures too. But people who work with lead are still getting some contamination. But at least for the general population, the lead in gasoline and paints are the main drivers, and lead water in pipes, which unfortunately still occurs in some parts.
So,
but anyway,
yeah. Speaking of lead contamination, like you were mentioning your fishing earlier, and people handling like lead weights and stuff like that, and then you're obviously using your fishing tackle in the water, and does that kind of contaminate the water? I mean, I'm sure not like, I think you would, if you had to use more lead waste maybe, but like, it's
Yeah,
kind
that's
of considered to think.
that's probably, you know, minimal. And I know that now I've noticed that all the fishing lead weights are all covered now. And in fact, all the lead that is used now is covered with something, other plastics or other type of metals. We have a detector actually now in Science 1 that has huge lead, and it's called cover with copper. You think it's copper, but it's not. It's actually lead. It's just cover for protection. And we have actually lead bricks in the lab, in the radiation lab. We have the Physics 137. We have a lot of lead bricks, and we did cover them with plastic, and you have to maintain that. So, you know, even if you touch them, you get, you know, you don't get any lead.
So there's still like foods out there like apples, the balsamic vinegar that protects their salad dressing that's actually is in lead barrels or something. There's some lead in the barrels that actually has it like on the label, very small, that it's
Yeah,
lead.
I think apples are one of those plants that also take quite a bit lead. If it's lead in the soil, they tend to uptake it more than other fruits or say. So yeah, I think apples are one of the one to uptake heavy metals in general, like if you have mercury or lead. I know in Romania there's, I think, a big apple orchard somewhere in the northeast, and they were exporting them to Germany or something, and they got ejected because their levels of, I think there are a bunch of lead mines and other non-ferrous metals in the north, and I think because they're not careful with that mining, I think they affected the local orchards. So they, yeah, they were not obviously watching those very carefully, but yeah. I think now food is usually pretty well measured in general, but water tends to, for some reason, still from, well, it's accidental, but it's, you know, still a concern.
Well, water is like really hard to manage. There's so many things. Like I think like mining causes that wash of mercury, lead, and different things from the soil into there. Like that's why it's like certain like mining programs that are like not only dangerous to environmentally, the situation environmentally when it comes to like protecting forests, but it also just harms the local people around it because of the wash of like water or like the dams or stuff like that. I think there's a quotium in the biology that was talking about that of mining in Ecuador.
Yeah, yes, especially in countries where, like, you know, there are probably laws against this, but they're not necessarily enforced or followed. So that's still, so yeah, some exposure to lead still occurs even for general population where, you know, there's not as much enforcement or, you know, of rules. And yeah, unfortunately that still happens. Yeah.
Okay, so more questions? Okay, well, if not, let's thank Mihai again for a great talk. And have a good weekend, everyone. And Mihai, we'll see you.
Yeah, a good weekend.
In 5 minutes.
See you soon.
Okay.
Bye.
Bye, everyone.
Okay, bye. Thank you, Dr. Mihai.
Bye. See you.